Morning students, this is K. Praveen Kumar Yadav, Assistant Professor, Triple Department. In this video, we will discuss about the Lenz law and Ohm's laws. We have a small idea about Ohm's law, but again I will discuss here. First, we will discuss about Lenz law. Lenz law states that the direction of electrical current which is induced in a conductor by a changing magnetic field is such that the magnetic field created by the induced current opposes the initial changing magnetic field. Okay, it is very simpler, but the theorem statement is somewhat difficult, but we will explain in an animated by using an animated video. Here I have an animated video for explaining the Lenz's law. Okay, Lenz law is nothing but it is an important principle in electromechanical energy conversion. Previously we are discussing about Faraday's laws, Faraday's first law and Faraday's second law. Those are very important in electromechanical energy conservation, alage same as Fleming's laws. In this video we will discuss about Lenz law, so it is also very important one. In the figure we can observe that we are having three axes. The axis end one is a circle scope space, and this is a magnet here. By using this we can explain about Lenz law. Lenz law, simply I can say that the result is always opposes the cause. Simply I can say the result is always opposes the cause. For example, here we are taking three axes, x, y, z. Three axes are there. One circular scope is there, and another one magnet is there. This magnet is having north and south poles. This magnet is having north and south poles, and this magnet will produce the electromagnetic flux lines, and that electromagnetic flux lines is here. Electromagnetic flux lines is passing through the circle shape. In that circle shape, it is nothing but a coil or a ring or a conductor, we can assume anything. So whenever the electromagnetic flux lines is passing from north pole to, that means this magnet, to this circle shape, in this circle shape it is a conductor. Whenever a flux is linked with the conductor, that means according to Faraday's laws we can observe that when the flux is linked with the conductor, there is some electromagnetic field, EMF, will be induced in that particular conductor, and that particular conductor is a closed path. Due to this closed path, a small amount of current will flow, and due to that current flow, that current will produce some magnetic field. According to thumb rule, we know that according to thumb rule, when a current passing through a conductor, it will produce a magnetic flux. By using the same principle, due to this magnet, the magnetic flux is linked with the conductor, and that magnetic field will produce a current, and that current will produce a self-magnetic field. Okay, these lines are indicating the self-magnetic field. Okay, now if you place this magnet as a constant, and the magnetic field lines is linked with this conductor, there is no change between linkage of flux lines. There is no change in the flux linkage. The EMF will be induced will become zero. Whenever the rate of change of flux is there, then only EMF will be induced in this particular conductor. For getting rate of change of flux, we have to change the change of linkage of flux. We have to move this conductor from one place to another place, that I already explained in the previous video. In that we can explain here. So this is Faraday's first law. That means why have to learn this Lenz law? Why we have to learn Lenz law? That means Faraday's first law states that how the EMF will be induced, and the Faraday's second law states that how much amount will induce? How the EMF will be induced is depends upon the Faraday's first law. That means whenever a conductor, whenever a variable flux, change of flux is linked with the conductor, the EMF will be induced. That is Faraday's first law. It will discuss about the EMF induced. EMF induced, and Faraday's second law discuss that the magnitude of the induced EMF. That means the rate of the EMF will depends upon the rate of change of flux lines. Rate of change of flux lines. So these two laws are indicating that how the EMF will be induced and what is the amount of flux. But these two laws are not discussing about in which direction the current will flow, in which direction the EMF will be induced. Okay, so that principle will be discussed, that condition will be discussed by Lenz rule. Okay, so you see here, this will discuss about EMF, and okay, so let us see here, when the current is flowing like this in one direction, it will, for example, it will say it will north pole. When the current is flowing in reverse direction, it will say as south pole. What happens? What happens when the current is flowing in any direction? Why you have to measure the current direction? Means if the current direction is changes, if the current direction is clockwise direction, it will produce a south pole. When the current direction is anti-clockwise direction, it will produce a north pole. If the poles are changing, the total characteristics of the circuit will change. So for that we can discuss about this current direction of the circuit. So for that, first we have to move this conductor. First we have to move this conductor towards the circuit. Let us just see here. I am moving the conductor towards the circle, means the magnet is nearer to the conductor, means more amount of magnetic flux is linked with the conductor. More amount of magnetic flux is linked with the conductor. When this more amount of magnetic flux is linked with this conductor, it will also producing the magnetic field. It will also producing the magnetic field. This one, these lines are magnetic flux lines. Then we have to know here also, that means in that conductor also, according to this magnet, in that conductor also it will produce some magnetic poles. In what pole will produce here? What pole will produce here? So this magnetic flux is produced by the north pole. So here this conductor will produce north pole, because here the north pole is nearer to the conductor, the circle conductor. South pole is far from the circle conductor. For that, north pole under this magnetic flux is under the north pole. For that reason, here it will produce a north pole. Here it will produce a north pole. Just see there. Here it will produce if the south pole is there, that means if the south pole is there, this coil will produce a south pole. So in the magnetic field is produced by the coil is due to this north pole. For that reason, this coil will produce north pole. If the magnetic field is produced by the south pole, then the coil will produce south pole. Here the coil is nearer to the north pole. For that reason, in this coil it will produce a north pole. So here this north pole and this north pole, this north pole and this north pole, both are like poles. So due to that reason, this north pole will repel this north pole. So due to this magnet will repel by this coil. Okay. So see here, this coil having one north pole, and this magnet is also having one north pole. These two north poles are repel each other. So due to that, this magnet is repelled by this coil. So this magnet is moving towards, that means moving towards out of the circuit. So like this, out of the circuit. See here what happens. Due to opposition of this north pole is again repel. That means it will move towards the outwards the circuit. So this like this. First initial condition, we are moving towards the circuit, and when we move towards the circuit, it will repel the north pole. Then the circuit will automatically repels the magnet. Then the magnet will comes out of the circuit. Okay. Again, the first when we move the magnet to the coil, there is a change in the magnetic field flux linkage. So due to that, the coil will produce the electromagnetic force, that means EMF, and it will pass the current and it will produce a north pole. And after that, when it will produce a north pole, it will repels the magnet. So due to that, there is a decreased rate of magnetic field. That means the magnet is moving away from the circuit. For that, the flux linkages will reduce. For that reason also there is a change, but it is in decreased range. For that also the EMF will be varies. So when the magnet is moves out of the circuit, then the coil is having some decreased range. Due to that, it will produce a south pole. It will, when the magnet is moving out of the circuit, then this coil will produce the north pole will be arising, and this coil will produce south pole. See here. This will produce south pole. Again, these are the two unlike poles. This is south pole and this one is north pole. These two are unlike poles. For that, the south pole again it will attract the magnet. Again the same cycle will be repeating. So in this video we can conclude that the direction of induced EMF is declared by the Lenz law, whether it is moving in anti-clockwise direction or clockwise direction, and the induced magnetic field in the coil is opposes the magnet. Magnet means here. Due to this only, here the current produced, and the produced current will produce the magnetic field in here, and the produced magnetic field again opposes this magnet. That means this is the result, this is the cause. The result is always opposes the cause. That is Lenz law. Okay. I hope you are having very good awareness of this Lenz law. Okay. Just go through the statement once again. Now you can having a clear-cut idea about this Lenz law. Now we can move towards the another law, that is nothing but Ohm's law. Ohm's law is nothing but okay, in this video we will discuss about this Ohm's law. For the next video we will discuss